Okay, we'll just cross our fingers that the audio is working. It didn't look like it was, but we'll just cross our fingers there. Okay, so here's our empty shell. And now we're going to draw, we're going to mark off delta x intervals first. Like this. So we have delta x intervals. Imagine x increasing through delta x intervals. And so for some delta x intervals, say this one right here, we want to draw a strip, right? A two-dimensional strip in the region, and rotate that strip the same way we rotated the region to get the cylinder that we're going to be used, a typical cylinder that's going to be used to fill this thing up. Okay, so for that, so the strip, then we'll start here at the start of the interval, and then if x is partway through the interval, we'll be to here. Let's just draw it again here like this. So the strip looks like this. And what's the width of that strip? If I'm partly through the current interval, the width of that strip is?
dx.
dx is the width of the strip. And dx is growing from 0 to delta x. And so when we rotate that thing around the y-axis the same way we rotated the outline around the y-axis, what do we get? What do we get? Do we get like a washer or a disc, or do we get like a shell or a sleeve?
Shell.
Yeah, it's going to be a shell, right? So it's going to look like this. And the current interval, how is that growing? By rate or by height or radius in the current interval?
Radius.
Radius is growing, right? The radius, the outer radius is at the x coordinate, and that's growing. And so what we're making the toilet paper roll bigger, right? By increasing x, it's like we're getting new layers of toilet paper on that thing. So the radius is growing. And so our rate of change is going to be?
The area of the lateral side.
That's right. It's going to be the 2 pi RH. Okay, and so we've had this question come up about, is the rate function going to be a piecewise function or just a single rule, right? Is it going to be a single rule, or is it going to be broken up into piecewise? So the way we can find that out is we start at the current value of x, and we imagine x increasing through these intervals, and we think about these strips and these cylinders. As we're going across, is the height, the way the height is defined, is that going to change somewhere along the way? And the way that the radius is defined, is that going to change somewhere along the way as x increases? So our first strip is here, and then we got the typical strip that I drew here, and then there's like these little teeny strips here at the end. So let's start with the radius. So what is the radius of these? R equals x coordinate, y coordinate, big change in x, or big change in y?
X coordinate.
X coordinate, right? Because we're rotating from the y-axis out to there, so that is simply the x coordinate. And is it the x coordinate the whole way, right? So starting at x equals 0 all the way out to this intersection point, is it the radius, is the radius the x coordinate for all of the strips? And the answer is yes, right? So for all these cylinders, that radius is going to be the same. It's going to be the x coordinate, starting from the most narrow, skinniest, tall one to this widest, short one out here.
I have a question real quick.
Yeah, sure.
So had there been the line x equals 1, then it would have been a big change in x, because we're no longer rotating from the y-axis.
Right, we'd have like this plug would have a hole in it, right? Exactly.
Cool, okay, yeah, just trying to make sure.
Sure. And then, so what about the height? Does the height stay, what the height is bounded by what? The curve on the bottom and the line on the top. Is that the same way the whole, for all values of x? Is it always the bottom, this curve, and always the top, this line. And if it is for all values of x, then we'll just have one rate function. It won't be split up by height. So, is it always the curve at the bottom? And is it always the line at the top for all values of x, starting from 0 out to this intersection here?
Yeah.
And it is. So our height is going to be, is this an x coordinate, y coordinate, big change in x, big change in y?
Big change in y.
Big change in y, right? So it's going to be a y final. It's going to be a greater y minus a lesser y. So I call it y final minus y initial. And what's y final? Y final is the y coordinate on this line. 1/2 x plus 3. And y initial is going to be the y coordinate of the curve down here. So I got my rate as a function of x. It's not piecewise because the whole way for all values of x through here, your height is always defined by from the curve up to the straight line. And the radius is always defined by the x-coordinate for all the intervals. Okay, questions on x? Okay, so let's rewrite, let's do...
Professor, I have a question.
Sure thing.
How did we decide that it was going to be the area of the lateral side and not area of the base? Because isn't x radius
Yep.
in this case?
Yeah, x is the radius. And in the current interval,
Uh-huh.
x is growing through a delta x interval. What does that change about this cylinder as x grows?
The radius?
Yeah, the radius.
So why did we decide on the area of the lateral side? Wouldn't it be area of the base or so if it's radius?
No, so I think you just got them mixed up. If the
Okay.
radius is growing,
Right.
so if the radius is growing, what part of this thing is adding volume? The side or the top?
Well, the side. 'Cause
The side.
Keep,
That's how you remember. If the radius is growing, then the side, the curve, the circular side is adding the volume. So therefore, the rate of change is that side.
right. Okay. Thank you.
If you're growing in height, where's the volume being added?
The base or no
The top
Yeah.
or the base. Yep, base and the top are the same thing. So the volume's being added here.
Mhm.
And so since the volume's being added there, that's where the rate of change is. That is the rate of change.
Thank you.
Sure. Okay, so let's try this in terms of y. So in terms of y, we've got the same situation. Okay, but now in terms of y, we're doing delta y intervals. And that's all the way up to the top here. Okay, and so a typical strip then in our delta y interval is going to look like something like this. What's the height or the thickness of that strip?
The height?
The little height here of the strip.
Delta Y intervals.
Delta y intervals, but this strip is growing in a delta y interval, right? It starts here and then this thing gets thicker in the current interval. So what's its current thickness in the interval?
dy.
dy, right? dy is growing. This strip is getting thicker, and then when you get to the next interval, it starts as a flat line, and then it grows and gets thicker in that interval. So y is like the top of the strip. It's the top of the strip. Y is increasing, dy is increasing. Okay, and so then we're going to rotate that around. When we rotate that around the y-axis, we'll get a disc like this. And so what is growing about our cylinders? This is the y-coordinate, is the top, dy. So what's growing? Is this thing growing in height or in radius?
Height.
Definitely going in height, right? This is going in height, therefore rate of change is?
Area of the base.
Area of the base, pi r squared. And what is the radius?
X value.
X coordinate, y coordinate, big variation in x, big variation in y.
A y coordinate.
X coordinate, right? So it's the distance. X coordinate is the lateral distance, right? So it's going to be pi x squared, but we need that in terms of y. Well, what is x squared? So we could solve for x, but we could just also notice that, look, what is x squared?
Y.
It's just y. So we just, instead of solving for x and then plugging it in, we can just notice, oh, look, we need pi x squared. Well, x squared is equal to y on that thing. Okay, are we done?
No, the rate of the radius changes at y equals 3.
Good. So here is a case where things change along the way. When we get to 3, what happens? So looking at this delta y interval up here. So at 3, now our strip is this. Is that strip, does it have the same radius as this one?
No.
No, because this one, for all these delta y intervals down here, these strips started at the y-axis and went out to the curve. Now, starting at 3, when y is greater than 3, our strips, they start at the line away from the y-axis and end at the curve. So we have a different, so this is for y less than, say, or equal to 3. Our cylinders look like that. When y is greater than 3, what do our cylinders look like now? If I rotate that around the y-axis, my cylinder looks like this. So I'm gonna have a piecewise rate function. For y less than 3, it's going to be this rate. But for y greater than 3, I'm going to have a different rate. Why? Because I have a different area of my base. So now, this is true for, so ry is going to be a piecewise rate function. It's going to be pi y when y is less than or equal to 3, greater than 0. But now it's going to be, for this part down here, it's going to be pi r outer squared minus pi r inner squared, because I have the hole in it. What's my outer radius squared? Well, that's the same as this one, right? So the outer radius is following the same thing as before, so that's just going to be my pi y. But now I have this inner radius. The inner radius is what? The x coordinate according to this line, which is what? Y minus 3 times 2. So x is 2 times y minus 3, and that's going to be squared. So 2 times y minus 3 squared. So this now is my second piece to my rate function, and that's for 3 less than y less than or equal to whatever.
Can you scroll just a little bit?
What's that?
My screen's just cut off. You could scroll down just a tad.
Well, I'll rewrite it again here.
Okay, thank you.
Oh, can you see it now?
No, I just thought you said you were gonna rewrite.
Yeah. Okay.
No, I think it's because like on Zoom, the bottom part of our screen has like participants chat, their screen, all that. So
Can you see that now?
Yeah.
Yes,
Okay,
that's
so
fine.
this is the rate function when y is between 3 and whatever this intersection is. What is this? 2? Is that 2? Is that 4? That's y equals 4. So the intersection, that's 2, 4, so that's 4. Okay, so we have to move on here. But so here, this is an example, because as you go through y intervals here, you have these strips based on starting at x equals 0, but then when you get to 3, the rate of change function changes because now this line kicks in as an inner radius that you didn't have before. So now your cylinders look like this. So let me show you. Okay, so notice. So the strips are going in delta y intervals down here up to 3, and we're getting the flat discs like this, the filled in discs. But as soon as we hit 3, and now our strips are just between the line and the curve, and now we get these washers for the last part. So
Mark, should that be pi times 2 times y minus 3?
Yep, thanks. Because it was 1/2 x, thank you. Okay, so does this make sense? So seeing those strips make the solid discs, but then at y equals 3, now we get the washers that have the holes. And that, since we have a different type of cylinder starting at y equals 3, we need a piecewise rate function. Pi y less than 3, and then this one greater than 3. Okay, any questions?
Just
question.
how did you get the the inner radius value? Is it from?
It would be the x coordinate on the line.
Okay.
Do you see that? So it'd be from here to here. What is that? That's the x coordinate
Right.
of the line. And then
Right.
so I had to solve for x.
Yeah, I get that.
Other questions?
For the expression you made, is it supposed to be pi y squared, or is it just supposed to be just pi y?
Well, it's pi x squared, right? So this is our radius is an x coordinate. So the radius is x. So then the area of the base is pi times x squared. Right? The radius is x. But x squared is y. We need it in terms of y because our independent variable is y. Did that answer it?
I see.
The radius is x. The radius is not y. The radius is x, so x squared is in our formula for area of the base. But we needed to write it in terms of y, so x squared equals y.
I have another question.
Sure.
So I remember during like some of the last couple of lectures, you would ask us like, okay, if we were to integrate, would half of it be if we were to integrate halfway? So in this situation, whenever we have a piecewise, is that a good indicator that it wouldn't work? Or like in this situation, would it?
What work? What do you mean work? What work?
If we were to integrate halfway.
Okay.
Like,
so if we were to take the accumulation of volume up to 2, you say? Because this is 4.
sure, yeah.
Okay.
That wouldn't work. I mean, it
I don't-
doesn't
what-
look symmetrical. Based
What do
off
you mean
the
by
eye,
work?
but,
When you say work, do you mean that this would be half of the total volume? Is that what you mean?
yeah. Sorry.
Yeah, we just can't tell here, right? So because this is,
Okay.
there's just no way to tell, which volume you would get, which is bigger. I mean, it looks to me probably like this, the second half would give you more volume.
Okay.
So very, very unlikely that these are going to be equal, right? Because this is, yeah.
Okay.
We don't have,
So we're not
there's
gonna-
no symmetry at all here. So there's no symmetry. So those questions we asked that before, we had some kind of symmetry going on. So we could make a determination. Here there's no symmetry. This is a very different cross-section than this is. So there's no symmetry there.
Got it.
And
Okay,
just from an
thank you.
eyeballing it, it looks to me like you're going to get more volume on this top half.
So that's not something we're going to be asked on an exam. Like, we're not going to give us this piece and ask us if it's like volume-wise.
The earlier questions, when we could make a good determination,
Okay,
that would
but
be
not
fair
like
game.
ones like these.
Okay, yeah. Okay, other questions?
Will there be a lot of questions that ask us to either visualize or write or draw like strips around the x or y intervals?
This is yeah. We've been doing this for over a week now, so you have to know how to do these problems without the nice animations.
Awesome, thank you.
You're welcome. All right, let's move on. We're running low on time, so let's see. So the next topic is arc length. Let's see, where am I? Where do I go? Here. And so here's just a kind of a motivational thing. So suppose this is a top view looking down on a stadium, and suppose we want to know how much siding we're going to need around the arena's perimeter. So it's like around the stadium or something like that. So the idea here is we're going to model that curve with an equation or a function, and then we're gonna calculate the arc length around that. So we want to do arc length, and so if we want to write an accumulation of arc length function, what are we going to need? If we want to write an accumulation of arc length function, what do we need for that? Oh, please, somebody know this.
A rate of change.
Right, we're going to do the rate of change of arc length, right? So because we've got the basic generic template for accumulation function, what does that require? The rate of change function for whatever quantity we're accumulating, right? You know how fast a quantity is changing at every moment, right? You know the rate of change. You want to know how much of it you have at every moment, the accumulation of that quantity, okay? So, here's an example. So here's an arc length according to some function, some crazy sinusoidal function, and we want to know what's the distance along that arc. Like if you were to walk it, how far would you walk? And so what do you think? Would you walk 6 units, 7 units, 8 units along that? What would you guess? In terms of these x-axis units, how far would your walk be if you walked along that curve? Or how long would that piece of string be, that purple piece of string? So we can watch it stretch out here, and maintaining the length, it ends up being 12.9 units. So that is actually the whole length, almost the whole length of what I'm showing there in the x-axis, the length of that. So we need to come up with a way to determine the rate of change of arc length. We want the rate of change of arc length so that we can write the arc length accumulation function. So here's how we're going to do that. We're going to look at, we're going to do very similar to what we've done before. Okay, so what we're going to do, so here's a function. It's a quadratic plus a cosine function. And what I've done is I've broken it up into intervals. And watch what we're going to do. So we are going to let x increase through those intervals, and as we do that, we are going to send off what? We're going to send off a tangent segment. We're going to pick off the slope of the curve at the left side, and we're going to maintain that slope, right? In each interval, we're going to have a constant slope. And so you see all those red segments. And so all those red segments are going to be what we accumulate to simulate this arc length. Is this going to be with the way I'm showing it here? The length of these segments going to turn out to be a good estimate for the blue arc length?
No.
No, right? It's pretty bad. As soon as you start moving away from that left endpoint, like for instance, this length, who knows how close it is to that actual arc length. Same, look at this red length is way longer than the actual blue length in that interval. So how are these red segments going to become a good approximation for the length of the blue curve? How's that going to happen?
Make the delta x interval smaller.
Right. So what I got? 0.3404. So look, if I make them smaller, can't see them anymore. Right there. Now these red segments. These red segments now, the length of those red segments are doing a much better job of mimicking the length of that blue curve. And the smaller I make the intervals, the better and better it does. Okay, so this should feel familiar. Kind of walked through this kind of thing before.
So for this one, we're doing tangent lines, right? And how come for the other ones we were doing, we just like estimate the average?
Because we're just going, remember, we estimated the average at first, but then we used the left-hand method, right? We said, let's just pull off the rate of change, the left-hand side of the interval, and make that constant through the whole interval. That's exactly what we're doing here. We're taking the slope of the curve at the left-hand side and making it constant for the whole interval.
Okay.
So this is very similar to what we did. We did the eyeball average method, and then we did the left-hand method. This is just like the left-hand method.
Okay, this is the left-hand method, but then we're like using a tangent line.
Yeah, because the quantity we want now is arc length, right? So we're going to be accumulating the lengths of these segments to try to mimic the length of the blue curve.
Oh, okay, all right. Sorry, just trying to.
No, that's good.
sort of
No,
refer.
that's good. I'm sure other people are thinking the same thing. All right, so let's talk about some different quantities here. So what's this quantity, right? What is this quantity, which is the same as this up here? And what's this quantity? Length. And then what's this one here? So can you tell me any of those? So for instance, this width right here, what do we call that? Which is also this one here.
Delta x.
Those are our delta x intervals, right? Those are our widths in terms of delta x. So this is delta x. So turn that into a delta x. Not bad. Okay, so that's delta x. And then what about this here? How far we've gone in the current interval?
Is it dx?
Dx.
Dx, right, dx. And so we've gone that far in the current interval. Look, in proportion to, if we maintain a straight line segment here, then we're maintaining our proportion with this length, which is what? So we have dx, and this would be the corresponding
dy.
dy. Right? So, and we know, and what is dy equal to? If we're maintaining a proportion of dy to dx, according to what the slope of this segment here is staying constant, then dy equals what?
mdx.
mdx. Staying in proportion to dx. And so, what? Because we have constant rate of change. We're assuming a constant rate of change according to the rate of change at the beginning of the interval. And what rate of change is that? If we're pulling off the slope of the tangent line to be our constant rate of change in the interval, what is that? It's the slope of the tangent line.
The derivative of the function.
Yeah, this is the geometric interpretation of derivative is slope of the tangent line or slope of the curve. And so it's going to be f prime of, now, which point? It's not just f prime of x, because it's f prime of what? The x value at the start of the interval, and we call that left of x. So for all these x values in this interval, left of x is this x value right here. And we want to pick off the derivative or the slope at that left x. So f prime at left x. And that's our constant rate of change for the whole thing. Okay, now this is what we're after, right? We're after that length right there. And so S is what we use for arc length, the symbol for arc length. So what would that little segment be right there? What is the length of that segment? If S is our general variable for arc length, then what is that? Right, so we have a dx here, a corresponding dy here. Therefore, this would be
dx squared plus dy squared.
It would be
Radical dx squared plus dy squared.
okay. Great. So let's write that. But then in terms of, so what's the point? The point is to get arc length. So what is this thing? What is it equal to?
That arc thing?
ds. It's a little arc length, right? It's a little bit of arc length, ds. Doesn't make sense. And so then what do we need? What do we said? We need the rate of change of arc length. Using all the symbols that are on the screen, what would we write that would represent the rate of change of arc length if we let x be our independent variable?
Could you repeat that, please?
So using the symbols on the screen, I want to use symbolic notation to represent the rate of change of arc length using x as my independent variable. So what should I write? What is the rate of change of arc length?
Is it radical dx squared plus f prime of left x?
I'm not looking for a formula yet. I'm looking for the notation that we're going to use that represents rate of change of arc length. Notation.
Do you mean
R subscript S of x?
Okay, so I think someone said it. Someone was close and someone said it, I think. ds dx, right? It's the rate of change of arc length, where x is our independent variable. So this is where that's going to come from, right? So you said that ds is the little hypotenuse, which is square root of dx squared plus dy squared. And from that, we're going to work out what ds dx is, knowing that dy is m dx, or f prime of left of x dx. All right, so what is our dy? Our dy is m dx. We're staying in proportion here, constant rate of change. So we're going to use the rate of change, the derivative at the starting point, dx. That's going to be our dy. And then we're gonna rearrange this thing to get what ds dx is. That's our rate of change of arc length. Okay, let's do that fast here. I'll show you in the text. Don't try to write this down, just watch and write it down later. So here's this. So we said ds is square root of dx squared plus dy squared, right? That's the length of the hypotenuse. And so then we're going to solve for the dy. We're going to put in the rate of change of f, or f prime, at the left side. We're going to put that in for dy. Now we have dx squared. We're going to factor that out and take the square root of it. So the dx comes out here. And what's left inside is 1 plus the derivative of f at the left side squared. And so there, look, ds equals rate times dx. Therefore, this is the rate, or ds dx. There's our rate. when things get small, right, what does left x become when the intervals become really, really small?
We just take it out.
Yeah, it's just going to be x, right? When the intervals get really, really small, it's like we're just taking every x value. So there's our rate of change of arc length. The rate of change of arc length is the square root, so if of function f. So we're graphing the curve of f, and we want some arc length, starting from A, say. I'm going to do an arc length function. So to get the rate of change of arc length of f, it's going to be the square root of 1 plus the derivative of f squared, all under the square root. Okay, so don't write all this down, but write this down. The rate of change of arc length of function f for the curve of f is the square root of 1 plus the derivative squared, all square root. And that came from what our little hypotenuse that we're measuring the length of is the square root of the dx squared plus dy squared. Any questions before you jump to the quiz? Okay.
Yeah, I have a question.
Sure thing.
Sorry. So where did this? I see there's two dx squareds in there.
Mhm. dy is
where did
mdx.
The second one.
dy equals mdx. And then we're squaring it, so you're gonna be squaring mdx.
Oh, okay.
You
Yeah,
see it?
I see it. Thanks.
Cool.